So I'm sharing the screen. Okay, so my talk is how can we achieve ubiquitous connectivity? So we have been discussing this I think for maybe 30 years, and we are not still there. So now, okay, I think we all know about me. So I skip this slide, and I want to show you where we are with 5G today and what we target by 2025 to in terms of connectivity, connected devices. That has been extracted from two important contributions. One is from the GSMA, the other one from GSA, that the organizations of the carriers and the vendors. And what do they say? So look at the prediction in terms of connections. Today, 5G is definitely on. So we have more than 230 million people really enjoying those services, and 86% of this population resides in China. China will continue to be the largest market by 2025, where we're expecting to have about 20% of the world population connected using 5G. And China still will be the one providing most of the services in terms of the connected individual, which is expected to be 45% of the entire connected individuals. It's of course intended that it's not just about China. Actually, if you look at the percentage of the penetration globally, we have that the North America, together with the Europe and Asia Pacific region, will account for 90% of the 5G mobile connection forecast by 2025. And North America will basically be the one mostly penetrated, connected 220 million people, which is around 50% of the reachable population. Now, in terms of devices, their study report is of last month, so from May. It is constantly updated, but gives an overview of the available devices. So commercially, you find already more than 430 devices, and here on the pie chart have the distribution proportion of the different form factors. You see still 50% around smartphones, but we have a variety of CPEs for fixed wireless access and a number of other type of form factors. And here I'm thinking of any kind of modules, onboard units, and for having the possibility of connecting any kind of device, not just smartphones, but robotic platforms, unmanned area systems, and so forth. Here you have the support frequencies we should pay attention to, because the frequency relates to the capability you're having to widely spread, so achieve an economy scale, those services. Of course, if you radiate like in Japan, US, at a very high frequency now coming, by the way, in Australia and Europe, I mean, the coverage is very restricted. So you have many complaints that they say, okay, look, I'm enjoying here outside my premises, outside this shopping center, 1 gigabit per second. As I am penetrating, I have an inter-system handover, or say a fallback to a service which really make impossible even to have a video call. So therefore, the majority of the deployments today are in the C-band, so we are around 3.5 gigahertz. And those are basically the spectrum largely supported by the different devices and the form factors. 3.5 gigahertz, 3.6 gigahertz, anyway, the C-band allow us to achieve the same type of coverage as the LTE at 1800. That is due to two simple features that the 5G supports, or the new radio supports from day one. In the downlink, we have I skip the roadmap since we don't have time. And the earlier speaker that covered already, just spend maybe a few comments on this. So radiating the C-band at that particular frequency, what we have here is the system on a new radio optionally support those for the 4G radiates using beamforming and and also MIMO on top. So the beamforming, the downlink allow us to say achieve better coverage and have the same coverage as I said at the 1800, so we can reduce the size. In the uplink, which is in the reverse directions, we have many challenges because it is mobile. Transmitted this frequency cannot have the same coverage as a terminal operating at the 1800 in FDD. And therefore, what we do here is to have the coupling approach where the new radio can also support the same frequencies as the 4G system by either sharing them in a time-wise or simply scheduling properly the signal so we can achieve the same coverage. Right, so if you look at the system, how that evolves, I think the earlier speaker that have covered well all pretty much all topics. And maybe allow me to say something more about the announcements now coming with release the 16 and 17 and potentially also 18 and later releases. By the way, the narrowband IoT and DLT MTC, so larger band, continues in parallel. So all this massive IoT type of traffic that comes along with a 4G architecture will continue. It's not affected by the new radio. That technology will be there and it's going to be enhanced for a very, very long time, as we don't have a clear solution coming from and with the new radio, as we are thinking of different types of use cases and pushing this technology more towards non-terrestrial networks. NTN, that as earlier mentioned, but allow me to stress here, because of the non-terrestrial type of networks, we have been using them as a backhauling technology is still there. We want to have as an access technique. So that means me with my phone, maybe not this kind of phone, something similar, or it can be a stationary station. I need to have access to the services where I find myself here in Australia. If I drive from Sydney to Darwin, I should have that particular connectivity, and that connectivity can be achieved through a satellite system. They are coming along now in various configurations, and we talk about geostationary, yes, but they are not so interesting because of the latency and other challenges we're having in place. What's coming out very hot are the very low Earth orbiting satellites, because they allow us to reduce latency. And when you look at the latency to the orthodromic distance, which is larger than the link you may connect via satellite, I think we can stay well below 5 milliseconds. And that's not just about accessing the services, but will also allow us to have very, very, very low latency and support other type of devices. The coverage is beautiful because the footprint of a LEO is expected to achieve, I mean, those guys, they are running from 300 to 1500 kilometers altitude, and they are rotating in about more than an hour across the whole planet. They have a footprint now from 100 to 1,000 kilometers, which is exactly what we will need, for example, here in Australia. Along with that, yeah, they have mentioned net slicing, virtualization, coming also on the RAN. The MBMS also will be supported, and that is important for verticals as well, because the broadcasters are now struggling, like in some places, to deliver a very high quality resolution multicast or broadcast system signal, and that could also come through the new radio. And then, of course, the security, which has been announced with respect to the 4G, will be further improved in terms of both security controls and assurance. The positioning, thanks to the trilateral way of mixing and matching the signal, we go down to 3 meters and 30 centimeters, which is extremely important, because if you think of connecting big objects, robotic platform, and maneuver them, or anyway have a remote control on them, you cannot do that only through using a GPS system, because it's completely unreliable, and say the way the resolution and the accuracy into move those objects is absolutely infeasible and impossible to do. They have presented well already the operands, so the way we want to disaggregate the system, and the TGPP has already completely specified that, and then ORAN Alliance comes along with other interfaces. But as you heard from the earlier speaker, also the analytic platform, so the platform for AI applications, completely specified for the core network service source coming from the RAM. So we are pretty much there, and I do see plenty of benefits. So if you do some dimensioning, for example, by deploying a disaggregated system, you may see that the advantage, especially you will have, are to achieve large coverage areas at a lower cost and large utilization of the resources. On the other hand, if you are diluting the system, you cannot have then higher performance in terms of latency as well as in terms of capacity and speed. That's practically impossible. But as we speak, looking at the possibility of having large coverage, I think by disaggregating the system, there will be advantages. And you may see here that in terms of connected radiating sites, we may shift from 10, where you are basically localizing the deployment, to a regional deployment of the central unit. We can have up to 100 sites, which may make the business case possible with a massive deployment of this disaggregated system in the rural areas, which is further facilitated by the introduction, which was not mentioned earlier, I think it's worth mentioning, by the integrated access and backhaul, because the spectrum is definitely a precious resource and not really available everywhere. So which means that if I am able to get my spectrum and I can use it for access, the same spectrum I can then use for access and backhauling using this feature, completely standardized already in release 16. Then here we have also an evolution of the device-to-device communication, which starts completely supported, beautifully supported by the LTE, further enhanced with the introduction of new radio. And then, of course, as the new radio enhances its capability and features, we have also, I think, by 2030, the possibility of discussing and enjoying advanced and full automation while driving or while, say, moving a different type of object and machine, also facilitated by the fact that there will be plenty on board radio units that will facilitate this communication. Now, I have just a couple of slides to summarize what I have presented, but also what I think the earlier speaker disclosed extremely well, is what I am expecting by 2030 is this type of reference architecture, which would allow us to achieve a ubiquitous connectivity. So without entering into the details, we will have the possibility of enhancing our new radio. I'm thinking of release 17, hopefully supporting the unmanned area vehicles or systems, but perhaps the new radio advanced, so means release 18, 19, and then we will start talking about 6G. What we are expecting here is to achieve ground coverage, air coverage, and space coverage, currently presented as a two-dimensional coverage. I'm coming from network design, so I have designed many networks globally. So our job was to say, okay, give me your inputs, and then on a map, to the map, I go through and I display the coverage, capacity, quality, parameter, and so forth. There we will achieve much more than that. So the target is to achieve this performance in a 3D, 3-dimension. And that is possible because you see how the system will evolve with the 5G and 6G, 5G already, let's not go too far, but even the LTE, if you have a proper design of beamforming, we can radiate and connect plenty of objects. So objects that would allow us to achieve not only coverage and use that as an access technique, but would allow us to integrate the system. We discussed about disaggregating the access, and that will also evolve not only on a terrestrial network. The access is going to be disaggregated all over the places, potentially. And you may see here that this will allow us to backhaul the communication and also front haul the communication using features connecting different type of objects, not necessarily, say, deployed on the ground, but on air, and that you have UAV aircraft and on the space, using especially the LEO satellites, that the range from 300 to 1,500 kilometers. Now, when you put your hands in practice, because I've tried to consolidate these things, you may see that the technologies and the players and the business models are very fragmented. I tried to map on this table the most important development technologies from Wi-Fi, LoRa systems, and then of course cellular terrestrial technology from narrowband and broadband type of machine communications up to the LTE release 14 and then 15. Of course, we talked about the new radio release 17, etc. It's very fragmented, and so what we could, I hope if we had time now, I'd like to discuss with you. I will see the possibility of integrating those systems, or how we could say what kind of technology could be exploited to really achieve a ubiquitous connectivity. And in my view, I think that could be done by first would require to go down in frequency, unless you don't want to complement some return to here. If you go down in frequency, then I think on the ground system, terrestrial system, down in frequency means playing with the 700 megahertz. Australia now it's 850, 900 megahertz, where we'll have I think a set range of around maybe 30 kilometers. But still, if you have a footprint of 100 to 1,000 kilometers, you really have a challenge to integrate those elements. Therefore, I think we need to have in place something more that on air and on space will allow us to support a front hauling type of interfaces that has backhauling. And in addition, I think we need to have also an element of access to the services. Therefore, just in conclusion, I think that the fundamental enabling technologies and capability, I think it's about spectrum availability, We need to go down in frequency, and then we need to have a technology which I agree with the other speaker, the Wi-Fi. If you look at Wi-Fi, even Wi-Fi 7, 6, I mean, the cell range is extremely small, because if you want to enjoy the bandwidth, you need to transmit at least at 160 megahertz band, and that won't allow you to have more than 50 meters range. Therefore, the deployment of those systems will be extremely local on campus, but it's far from, say, I think, achieving a massive coverage. And then also the capability of having playing on unlicensed spectrum, which, by the way, will be also supported by the new radio in release 16. It is anyway limited. So I think spectrum is important. And when we go up in frequency, I think the only way for us to enjoy those services is to have different type of access points, because going up in frequency, the cell range, or anyway, the range of coverage, I've measured them, even in US, it is extremely limited. So you have a good coverage in line of sight up to maybe 700 meters, but then disappears when you go indoor, and then you cannot think of relaying or distance. So I think we need to introduce something that will be on air and on space. And here I think that the non-terrestrial networks will definitely make the difference, enable new business models, because there will be positive business cases, and practically integrating them, complementing them with terrestrial type of access network will allow us to achieve and say take the services or bring the services in areas where currently it's very hard to get and obtain any kind of signal. And the last thing, we need to find a way to bring the security controls and privacy. And I think here, the way forward, in my view, that's my personal view, we need to exploit the concept coming along with the 5G core. I'm not thinking of the core as an element, you may buy it, you may have it, some expenses. I'm thinking of the protocols that are coming with the 5G authentication and key agreement, or extending the protocol from the internet that is supported through the utilization of USIM, which means any device, that could be this, that could be like that one, it could be my pen, anything could be connected and authenticated, authorized, and with also a large degree of accountability, because we need to trace anything in a unified way that is already specified, standardized in release 15 with the 5G core, or better, the stack of non-access stratum and the corresponding end. So thank you so much, Kanesh. I think that was pretty much. If you want to know more about these things, I play a lot with, I'm on LinkedIn, I like to play there, and there I also sharing non-confidential material, which will be also this presentation available here. Okay, thank you.
Thank you, Prof. Thank you for the great insights. It was very valuable. Appreciate that. So yeah, let's have a quick 5 to 10 minutes Q&A sessions. If anyone on board have any questions from any speakers, please feel free to ask. Maybe I will start first. Professor David, I did realize on your last slide with reference to the architecture by 2030 was a quite interesting input here. There's one question that I'm still questioning myself, and maybe anyone could be able to give more info, which I'm lack of, in terms of the application platform in the architecture, right? So do we really have enough of applications in the market, in the industries, in the mobile operators or the hyperscalers that actually targets the the low latency requirements, the mission critical control requirements. As I realized, the 5G was very much focused to the industrial manufacturing or agriculture or even petroleum with the vast of IoT devices, connectors, and all so on and so forth. But when it comes to the consumer market, is 5G really tackling the consumer market? That's number one. I realized that when it comes to South Korea with the 14 million of 5G subscribers, and it's my opinion, maybe I'm wrong, but I realized that only South Korea out of this world who have really focused into the consumer markets when it comes to the augmented reality applications, gaming, VR. You know, they are the first guys who came out with the Pokemon many years back, right? So they have actually spending a lot of time into this application development, right? So how are there any other bigger operators or hyperscaler players are really focusing into the 5G, particularly on the low latency requirements, so on and so forth? Anyone can able to answer on that?
Well, I could start. Can you hear me? So basically, the reduction of latency, it is a fundamental enabler to all services. So that's an example of services to consumer, to home, and business to business type of applications. If you wanna deliver an experience like in Korea, South Korea, they're having, and I think that is the most important application for enhancing the mobile broadband experience. So I'm talking about the augmented reality, virtual reality, which can be applied to an unlimited number of use cases, from training, smart education, down to manufacturing, constructions, anything and everything. You need to reduce the latency. Otherwise, if you don't do that, it happens that you need to let all those capabilities in the device. Being the capability in the device becomes extremely expensive. So our target is, there is an example of a project that here in Australia has been submitted to the government to achieve what you say. Achieve what you say means even in Australia, start enjoying virtual augmented reality and create jobs, better experience. It is exactly what was presented earlier. You need to have a possibility of not only, say, make your interface more capable in terms of delivering good food. You need to reduce latency. In order to reduce latency, there's no other way than install the applications close to the device. That allows you two things. First is to incorporate, take all the expensive capability of the device, including the brain of a robot, and move that on the edge cloud. That's the first thing. The second, so that cost of this device is accessible to anyone, not only rich people, but any student can have the possibility of buying this kind of device, because the rendering capabilities as well as the interaction element will be in the cloud, the edge cloud, close to the edge. The other is the capability of reducing latency, and that will make it possible to have interactions between the individual and any service that could be here. So to me, this is a fundamental enabler that is the multi-access edge computing. And that requires, as I said, also a better way to transmit the signals at radio interface, because we must reduce also the latency here. We need to increase the speed, and we need to be reliable through multi-connectivity. Otherwise, those services would be then somehow discontinued. So that's basically what I think.
Yeah. Actually, let me reiterate from different angle, and actually exactly for the gaming and for the